Yours?
Thanks for the introduction. Can you hear me?
Yep. Perfect.
Oh, thanks. Yeah, hi everyone. My name is Yiming, and I'm a second-year PhD student at NYU, and also a research intern at NVIDIA Machine Learning. So today I'm very happy to talk about collaborative and adversarial 3D perception for autonomous driving. Autonomous vehicles relies on 3D LiDAR to capture the measurements of the environment. And then it needs to analyze such kind of irregular 3D data to perceive the surrounding objects in order to make safe decisions. However, there are several challenges in processing such kind of irregular data, such as data sparsity, partial full occlusion, and motion distortion. And in this talk, I will go over our efforts in two directions. The first one is collaborative perception, and the second one is adversarial perception. In these two works, we design. I will show how we design novel 3D deep learning algorithms to improve the robustness of the LiDAR-based perception system. In the collaborative part, we are trying to investigate how to conduct collaborative perception in a high-dimensional feature space, and we propose a matrix. We propose to learn a digraph with matrix value weight in order to achieve collaborative perception. So the motivation is simple. The single robot perception has several fundamental issues, like long-range perception and frequent occlusions. So multi-robot perception is proposed to solve the fundamental issues for single robot perception. And multiple vehicles can bring more viewpoints, so that each single vehicle could see further, better, and even see through occlusion. Meanwhile, there will be more computational resources available. However, to design a robust collaborative perception algorithms, there are several bottlenecks. For example, what information should be transmitted, and also how to aggregate the information efficiently and effectively. In other words, how to improve the performance bandwidth trade-off. Regarding the first question, what information should be transmitted, some methods use early collaboration. And in this work, they just aggregate all the raw point cloud data in Euclidean space. Then this kind of method has no information loss, but the bandwidth is expensive. And also some works propose late collaboration, which means that it just fuse the output of each agent. However, the fusion of the result from each single agent, which is not reliable, cannot result in a robust model. And recently, there are some researchers proposed intermediate collaboration. And instead of fuse the raw data or fuse the output, they propose to fuse the intermediate features of a neural network. And the advantage is that these features is easy to compress. However, the challenge is that how to design a collaboration strategy in high-dimensional feature space, because now we are now in an intermediate space, and everything is hard to, especially for a message with spatial resolution and with the post information. It is hard to design a robust collaborative strategy in high-dimensional feature space. And some previous works like V2VNet or one-to-a-com, they use graph neural network or attention-based mechanism to model the collaboration among different agents. However, there are some problems like latency issues. These two methods, all these three methods requires multiple iterations. So this will introduce a huge latency in the real deployment. And also the accuracy problem. All these three methods, they use scalar value weight for message fusion. However, this will lose the spatial information and fail to highlight the informative range and repress the noisy range. So in this work, we assume that multiple robots are located in the same area, and they can perceive and collaborate with each other without communication. And also each robot is provided with an accurate pose. And our goal is that given a certain communication bandwidth, which means that a certain layer of the neural network, we aim to maximize the perception ability of each agent by optimizing a collaboration strategy. And we introduce a fully connected digraph, and we propose a matrix value weight, and then we can convert the problem of collaboration strategy optimization to graph learning. And here is our collaboration graph. We assume that multiple agents are at the same intersection, and each agent can only perceive a certain area around itself because of the limited sensing capability. And for each node, it is equipped with an intermediate feature map and also 6 dot poles. And the age is directed, and age rate is matrix value. So our graph is fully connected, dynamic, post-aware, and also adaptive to perception measurements. And now let me introduce our collaboration graph procedure. Here we assume that the agent 1 is the ego agent, and it needs to aggregate the information from the neighboring agents, agent 2 to agent 5. And because all these feature maps are defined in their local coordinates, then the first step is to synchronize the coordinate, and we transform the neighbor agent's feature map to the coordinate of the ego agent feature maps. The next step is age weight generation. We use a learnable convolutional neural network, which takes the concatenation of the neighbor agent's feature map with the ego agent feature maps, and then output a matrix. And here in this matrix, it means the spatial importance of the message from the neighbor agents. If a pixel has a higher value, which means that this message is more valuable. And then we implement the pixel-wise normalization. And finally, we use a weighted sum to aggregate all the information together. And now let me introduce our learning strategy. Our intuition is that we want to integrate the advantage of early collaboration, which has no information loss, and the intermediate collaboration, which is easy to compress. And we use the knowledge distillation framework. And the knowledge distillation is generally used in model compression. But however, in our work, we just use a teacher network and student network with the same architecture, but the different input. The teacher network is based on early collaboration and takes the multi-view data as input. And the student network, which is based on intermediate collaboration, which takes the single view data as input. And we use knowledge distillation to firstly train a teacher network, which is based on early collaboration. And then let the teacher network guide the learning of the collaboration graph. And now let me show you the overall pipeline. And you can see that the top part is our teacher network. We firstly aggregate all the raw data in a Euclidean space. And then we input this multi-view point cloud data into the teacher network. And then for the student network, each agent will take the single view point cloud as input. And then it will implement a collaboration graph process in the intermediate feature space. And then we will input the updated feature maps into the decoder and output head to get the final results. And during training, we first train our teacher network just using the detection loss. And then we fix the teacher model and train our student model. For our student models training, in addition to the detection loss, we will add a knowledge distillation loss, which we try to minimize the feature maps after the collaboration and make these feature maps try to approach the teacher's feature maps. So this can guide our collaboration graphs learning. And to verify our method, we propose a new data set, V2XC. And we use Scala small cross simulation to generate the data set. And here is some visualizations in the bird's eye view. You can see that each color denotes measurements from an agent, and the orange boxes denote the vehicles to be detected. And our method has shown best performance amongst all these intermediate based methods. And here is something interesting for the qualitative results. You can see that in this figure, the green boxes denote the ground truth, and the red boxes denote the predictions. And you can see that for the agent 1 here, it has no measurements in the left bottom range, which is in the red circle. So in the self-age weight, which means that how important is the message, how important is its own message. You can see that here is our visualized graph age weight. And the darker color means lower value, because the agent one cannot perceive the left bottom range. So it will lower the confidence of the corresponding range. And however, for agent two, which has a complementary view, so it can perceive this range well, right? So for the edge weight from agent two to agent one, it can provide the complementary information for the agent one. So the agent one will highlight the informative range, which is the corresponding left bottom corner. So in summary, in this work, we propose the novel distilled collaboration graph for multi-agent 3D detection. And in our graph, we use a matrix valued edge weight to highlight a different range adaptively. And we also build a new large-scale multi-agent 3D detection data set. And we conduct comprehensive experiments to verify our method. And here I also want to mention that our current ongoing effort, which we try to develop an open source collaborative perception library. And our library can support different perception tasks like detection, tracking, and segmentation. And also we have integrated several state-of-the-art collaborative perception methods like DiscoNet, one-to-come, and DiscoNet. And if you are interested in the contribution to our open library, and feel free to send me an email, and we can definitely talk about that. Okay, now let's skip to the next part, the adversarial part. In this paper, for the LiDAR perception by adversarial trajectory perturbation, we try to investigate an overlooked vulnerability which lies in the motion compensation process. And we show that the only adversarial spoofing of a vehicle's trajectory can fool the LiDAR perception system. The background is that a deep learning-based LiDAR perception is quite critical. However, a deep learning is vulnerable to carefully designed imperceptible perturbation. For example, in 2D object recognition, you can see that if we add some very imperceptible noise onto this 2D image, and the deep learning model will misclassify the panda as a gibbon. However, for our human eyes, this picture is still a panda, right? So the adversarial learning is quite interesting, and several researchers have been investigating the adversarial learning in 3D computer vision. And for the object level point cloud attack, some methods propose to adversarially perturb some point coordinate to fool the 3D object for the 3D object recognition model. And for sea level point cloud attack, some methods propose to strategically optimize some adversarial objects and put them on the self-driving vehicle, so that can make that vehicle invisible for the detector. And also for some researchers propose some physical-based attack, and they strategically inject points into the scene, and this can make some impact on the driving behavior. So in summary, existing methods just try to manipulate the point coordinate in the Euclidean space. But our key observation is that actually for the sea level point cloud, the LiDAR points are functions of sensor trajectory because of the motion compensation, right? Because you can say that the LiDAR is rotated while the car is moving. So actually the different environments are captured at different time steps. And also they are in different coordinate systems. So the vehicle needs to aggregate all this information into a unified coordinate system. So we propose a representation for sea level point cloud, which is a trajectory based. And here the T denotes the trajectory, which is a set of transformation matrix. And the PN denotes the LiDAR package, which is captured at different time steps. And so after aggregation, we can get to the final full sweep point cloud. So instead of manipulating each point coordinates, we try to manipulate the whole trajectory of the self-driving cars in order to achieve the adversarial attack against the LiDAR-based perception systems, because the vehicle trajectory could be easily perturbed by spoofing GPS signals. And to achieve to verify our method, we need such a data set. However, for existing data sets, they have all implemented motion compensation before the release. So we try to simulate the motion distortion and correction using simulation with real-world data set. And here, let me take an example. Assume that we have two neighboring frames, frame A and frame B, and we can interpolate n steps between these two frames once we assume that the car's motion is smooth. And then we can separate the point cloud at frame A into n packets, and then we assume that the packet n is captured at the frame n, so that we can transform the points in packet n to the corresponding frame, and then we can get we can simulate the motion distortion and correction. And compared to the coordinate-based attack, our trajectory-based perturbation has several advantages. The first one is physical feasibility, because we can easily achieve the adversarial attack using GPS spoofing. And also we have better transferability because our method can even transfer across frames, because for the point cloud, each sweep has different numbers of points. But for the trajectory perturbation, actually, the perturbation has the same size, so we can easily transfer the perturbation across frames. And most importantly, our attack method has better performance because of the novel parameterizations. You can image that for the point cloud coordinate-based attack, it can only manipulate the XYZ locations, right? The translational part. But for the LiDAR packet, for the trajectory-based attack, we actually are manipulating the trajectory, and the trajectory is for the trajectory-based attack, we can now consider each LiDAR packet as a rigid body. And so we can also manipulate the orientation parameters of each LiDAR packet. So this will introduce more parameters, and we can have a better attack performance. And here is our results in the white box attack. And you can see that we can individually attack the translational part and the orientational part, and also the full trajectory, which includes both the translation and the orientation. And you can see that the false positives are gradually increased. And here is our black box attack, which means that we have no access to the model's parameters, and we just use the perturbation learned on white box model point RCN and transfer it onto the point pillar model. And you can see that the left one is the original detections, and here the predictions are denoted by red boxes, and ground truth boxes are denoted by the green color. And you can see that after attack, some boxes are missed. However, for human eyes, we can still find there is very imperceptible difference between these two sweeps. And to make our attack more smooth, we also implement a polynomial coefficient onto the trajectory. And instead of trying to manipulate each trajectory point, we are now trying to manipulate the polynomial coefficients after the interpolation. And then you can see that here is the original point cloud, and the second figure is the discrete trajectory perturbation. The point cloud after discrete trajectory perturbation, and you can see that there is still a little difference between these two frames. However, if we implement a polynomial trajectory perturbation, you can see that it is very hard for human eyes to differentiate these two LiDAR frames, because now the neighboring packets has a very small difference due to the smoothness constraint. And actually the white box adversarial perturbation can totally blind the LiDAR perception systems. You can see that the average precision could be decreased to nearly 0. So this raises a red flag for the community. Okay, in summary, in this work, we propose a simple and effective method for motion distortion and correction simulation, and we propose new representations for point cloud with respect to trajectory. And we also propose generic and feasible trajectory-based attack pipeline against LiDAR perception. And in the future works, we may want to study how to defend such kind of adversarial attack. Okay, that's all. Thanks for the listening.
Thank you, Yiming. Just I have a very simple question. Have you ever investigated an approach for your adversarial network that has ego motion monitoring already implemented? Basically, the trajectory-based disturbance, what you provide, right, wouldn't work if somebody has, or the platform has ego motion monitoring, and it has, let's say, a very simple model-based approach.
You mean that it can monitor the change of its motion?
Yeah,
right.
One cannot alter, or it can identify that such a change is not natural according to its domain.
Yeah. I think that's a very good question, and actually, I think that could be a potential adversarial defense mechanism. But in this work, our argument is that the trajectory perturbation is very, very smooth, and we add constraint on the perturbation. You can see that the maximum perturbation in each, it is 10 centimeters in translation, and it is very, 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 very small. And we assume that. Sorry.
Understandable. Thank you. But the point is, when somebody thinks about level 4 driving, the ego motion, the parameters are the quality expected is in sub-centimeter level, right? In translation.
Okay.
Just as info.
Got it. Thank you.
Any more questions? So I had a quick naive question. In the graph formulation, you said that this is a matrix valued edge. What does this matrix actually have?
What do you mean by the?
What are the values of this matrix? What do these?
The value of this matrix, right?
Yes.
Yeah. So for example, let me take this as an example. Here we have 5 agents, right? And we will have 5 feature maps, and then we want to conduct a weighted sum. So the weight is actually for the matrix validated weight. It has the same spatial resolution with the feature map. For example, if your feature map has a size of 32 by 32, then the weight also has the same resolution. And for each pixel, it will conduct a pixel-wise normalization. So to make sure that for each pixel, the sum of all these agents will equals to 1.
Okay.
Yeah. So it is a relative number, but not a absolute number for the weight.
Thank you.
Yeah. Thank you.
So if there are no more questions, let's thank the speaker.
Yeah, thank you.
And thank you, Yiming, for getting up early.
Yeah, thanks.
So the next speaker is Steve Han. So Steve Han is a deep learning engineer at Qualcomm AI Research. His research interests include